Hello everyone, my name is Muhammad Shahid Munir, a PhD student in Sangungan University. I am presenting today ION, Adaptive Embedding Optimized Noise for Robust Watermarking in Diffusion Models. This paper is accepted in WACV 2026. A bit about my lab. I am I am under Professor Simon Wu doing my PhD in Dash Lab where we worked on multimodal defect detection, anomaly detection, and machine unlearning, which is about right to unlearn. And we work on large language models and representation learning related to deepfakes detection. We have worked with different private organizations, and we are still working on different projects associated with Samsung, and we have the honor to work with Korean National Police Agency on combating drive of deepfake and detecting deepfake in public domain. My topic for today is ION, and which is uh, uh, watermarking technique. As we know, AI generated contents are becoming rapidly increasing and they are becoming more useful these days. People are using it easily and anyone can generate images that are highly realistic and hard to detect through naked eye. They are realistic and they are widespreading everywhere, and that's why we need a robust watermarking technique that do not compromise the image quality and also retains the watermark and can verify the authenticity and protect the copyright of the generated content. There are two different types of watermarking methods, post hoc methods and in diffusion methods. Post hoc watermarking methods embed watermark after the image is generated, while in diffusion watermarking uh, generates image watermark, embeds watermark during the generation process. So both types are vulnerable to adversarial attacks, and performance degrades when we combine different all of the attacks and mimic the real world editing. Adaptive watermark is embedded in Ion, while existing methods such as Robin embed a static uh, watermark that is visible when we embed in later diffusion space steps. So, what are diffusion models? Diffusion models are denoising diffusion probabilistic models that, given a noise, generate an image and reverse the image to noise and then train a model such that the noise is converted to image. Then they progressively add Gaussian noise at each different steps from let's say 1 to 100, and keep improving the image by adding noise. So this training involves reversing the process where we reverse first we generate image, then we reverse the process by creating noise from this generated image. So as we discussed, post hoc methods embed watermark later after image is generated, while indiffusion watermarks embed watermark during the diffusion process. Both have their drawbacks. Like post hoc methods have a edge on uh, improve a little edge on quality, while still the artifacts can be detected within them. While invisible indiffusion watermarks uh, is very robust to adversarial attacks, but still it has limited image quality. So ion consists of three stages, and in first stage we train hash network, in second stage we embed watermark, in third stage we verify the watermark. In first step we have a hashing network that is trainable, and we take in HT, that is intermediate noise, with T injection timestamp where we you take XT from intermediate noise, and then we use this XT to train the hash network, and with the hash network we generate a hash that is trained with different loss functions that will be discussed later. In step 2, we have adaptive watermark generation, where we use the same hash network that we train in step 1, and this hash network takes in HT, generates a watermark hash, and that watermark hash is then blended into the intermediate noise through Fourier transformation, and then IFFT operation, and then we continue with the further generation of the image. At the final stage of the watermark generation, intermediate image generation process, the watermark image is generated that is containing the XT watermark Fourier space within which is blended within the image and infused into semantics. We mimic a reconstruction attack, and the reconstructed image is then used. Let's say we use to extract W, that is the watermark noise, by using inverse DDM and FFT process that is taken from the Robin and existing methods. And then we compute the difference of this extracted watermark with the existing watermark that we have, watermark that we generated in step 2. In stage 1, during the training of hash network, we use different loss function, and to make sure that gradient flow we utilize state through estimator, and uh, the network utilizes flattening linear transformation and 10H activation to make sure that the watermark that we generate is semantically similar, and it has gradient flow. To we use ensure the structure and semantic similarity, we utilize cosine similarity loss, and to mimic the attacker during the reconstruction attack, we utilize FFT blending, and then we try to reduce that reconstruction. We used RET loss from existing method that retains the watermark better than existing tree ring method, and make sure that adversarial attacks do not disturb the watermark. This is the algorithm for hash network, which takes in an image and outputs hash. The first, we flatten the image, and then we pass it to a linear layer and apply our 10H activation function. Then we use STE, that stops the gradient from one branch and makes sure that gradient are flown, and the hash network produces a watermark that is semantically similar to the original latent XT. So this overall setup helps in generating a semantically similar hash noise and preserves semantic similarity with the intermediate latent, finally producing an output image that is blending a watermark into the latent space, into the image in semantics, such that it's not visible during the final stage. So watermark generation pipeline is the second stage, where we take in the same hashing network that we trained earlier to generate semantically similar latent noise. We uh, given a T injection in between latent step, we take in XT and give it to the hash network, then generate a watermark hash and embed that watermark hash into the blend into the HT, and then we forward it to the forward diffusion processes. This makes adaptive hash generation process, and XT is actually blended with the following equation that uses Fourier transformation. This hap this helps in because we are using an adaptive watermark strategy, which helps in generating a watermark that is similar to the latent noise, helps in minimizing the visible artifacts and preserving the image quality, as we see earlier later. In the intermediate, latent extraction follows by following DDIM process, where given an in previous image, we previous latent space xt minus 1, we generate predict xt. To predict that, we take a T injection step where we want to inject the watermark. We generate xt here. We take that xt and generate in second stage. We generate an adaptive hash watermark with the same loss function, that the same hash function that was trained earlier with the cosine similarity loss. Frequency domain blending follows by taking the same generated watermark and blending it to the xt, that is the intermediate noise. We continue the diffusion process further with that intermediate noise embedded into the uh, latent space with the watermark. So this continued diffusion process generates the final image. After getting the final image, we mimic the reconstruction attack and we get the reconstructed image, and we then use the DDM inversion as we discussed earlier, taken from the existing method like drop-in, and apply FFT operation to extract the noise, and then we compare it with the existing watermark that we saved earlier in stage 2. Then we compare it with the threshold comparison for authenticity of the watermark, and the this gives a robust extraction method process, and which helps in adaptive nature, and this adaptive nature helps in embedding watermark in the later stages. For experiments, we use diffusion model, that is V21 base, which is a guided diffusion model. For training hash network, we use MS Coco, and for prompt dataset, we use existing dataset, that is Kustoaska, from Robin and Treating, so that we can compare with them exact same thing. For generation parameters, we use 50 denoising steps, where we embed the watermark uh, at the stage 40 for better results. And guidance scale we take in 7.5. For image dimensions, we took 512 by 512 image dimension. We use DPN solver for noising denoising, and for we generated 1,000 images for the evaluation of the proposed approach. As far as the hardware is concerned, we use NVIDIA A140GB. We use hyperparameters. For alpha, we use 0 0.9. For gamma, we use 0 0.4. Hash generation training takes in learning rate of 5e minus 4 and batch size of 16 with the max step 2000 and seed of 42. To ensure the watermark presence, we use uh, performance measuring metrics like AUC for measuring the performance of all possible thresholds, and for accuracy, for we use accuracy for correctly detecting the watermark. We use TPR at 1% FPR for true positive rate when false positive rate is 1%. We use SSIM, which is structural similarity index, for computing the image quality to make sure that it follows the image follows the structure of the original image. We use peak signal to noise ratio PSNR for maximum possible power and noise. We used MSSIM for mul- that use that is the extension of SSIM to multiple scales. We use FID for measuring the similarity between feature distribution and compare statistics of real and fake watermark image. Here, lower FID indicates better fidelity. For prompt alignment, for the prompt to make sure that prompt generated image aligns with the prompt, we used clip score that ensures that indicates the better alignment of the image with the higher score. We use the attack scenarios where we take in the traditional degradation attacks, which includes noise brightness, crop rotation, and JPG compression. For reconstruction and adversarial attacks, we use BM3D, BM SJ18, Zahao 23, and Chang 20. These are the works that earlier used. We introduce another attack that combines all of these attacks and creates an image which is combined all of these attacks, and this mimics the heavy editing that the image goes through during the sharing and um, sharing the image on the social media and other platforms. Here, Ion shows robustness against all attacks as well as the cumulative attacks. Existing methods reduce their robustness when we test their model on cumulative attack that we present, and this combined attack actually reduces the AUC by 94 4% on Robin, while our method retains the robustness against that attack. AUC against different reconstruction attacks shows better performance than existing methods, and cumulative attack shows better performance than all other methods, while existing methods fail when we apply cumulative attack. To assess the image quality, we plot this figure where we can see that tree ring have lower image quality, but Robin, despite having a better image quality, it lacks the intrinsic details of the image. However, the Ion is giving better quality that resembles the original image more in semantics. The watermark quality reduces in Robin, where the watermark, when injected at later stages, shows visibility on different areas highlighted here. While Ion, since it embeds watermark within the image, uh, in within the image semantics, it actually fuses it and increases the image quality and retains the watermark when applied different adversarial attacks. We did some ablation study on different parameters, including the steps. When we embed watermark later steps like 35 and 40, the image quality keeps increasing and the robustness keep increasing. This was given by the Robin paper, where they discussed that when we embed watermark in later stages, we can preserve AUC and PSNR that we observe the same phenomena in our Ion paper. The key contribution of the proposed approach and the advantages are the novel adaptive watermarking, which embeds watermark in semantically similar noise, and then the noise is guided through the diffusion probabilistic model, and then we get a watermark image that becomes an intrinsic part of the image, which gives us a semantic alignment, and this gives us state-of-the-art robustness, superior performance on traditional attacks. This shows resilience against reconstruction and adversarial attacks, and also a cumulative attack shows better promising result in the proposed approach. The method shows high perceptual quality, where adaptive and semantically injected watermark ensures high quality, which maintains high perceptual quality without visible artifacts, while Robin, as we see, shows visible artifacts. This work effectively work on even when embedded in later diffusion steps, which makes the process better resilient against adversarial attacks and improves the image quality further. In future, we will implement different diffusion models like uh, stable diffusion XL and new upcoming stable diffusion like stable diffusion 3.1, and we will evaluate the proposed approach on that different models, and then we will implement the approach on defect detection and provenance tracking, content authentication, and copyright protection. The key contribution are as follows: as Ion introduces a semantically similar hash that is embedded into the image, and it shows resilience against different adversarial and traditional degradation attacks. It gives a high perceptual image that is very close to the original image. And that's all from my side. If you have any question, thank you for your attention. And if you have any question, you can talk to me, give me an email here. Thank you.